Welcome to this new episode of our Mysteries Day series. Today we are exploring models of consciousness, focusing on how certain architecture provide unique inductive biases that could lead to a generalizable form of intelligence, and perhaps even one day, artificial consciousness. My name is Guillaume Dumas. I'm an associate professor of computational psychiatry at the University of Montreal and the director of the Precision Psychiatry and Social Physiology Laboratory at the CHU Saint-Justine Azrieli Research Center. I'm also an associate academic member of MILA Quebec AI Institute and hold an FRQS fellowship in AI and digital medicine, plus recently been appointed as the CIFAR Azrieli Global Scholar in the Brain, Mind, and Consciousness program. Inductive biases are crucial in machine learning, particularly in deep learning, to develop higher levels of cognition. These biases are assumptions that help predict outcome based on new unseen inputs. A well-known example of such inductive biases is the Occam razors, which suggests that the simplest hypothesis is often the best. You might recall also the no free lunch theorem, which states that no single algorithm excels at all tasks, that was also raised at the beginning of this course. To improve performance in specific tasks, we strategically incorporate inductive biases into algorithms. Interestingly, some of those inductive biases relate directly to consciousness. Today, we will discuss how these biases are used in computational models of well-known consciousness theories. Thanks to Claire Sergent, you have been already introduced to the global neuronal workspace theory. I've worked on applying this concept biophysically with Jean-Pierre Changeux, one of the co-founders of this theory. We focused on biological inductive biases and their impact on learning mechanisms across the different levels at play in the theory. We found that the best architecture emerged as a complex interplay of Hebbian and reinforcement learning, but with the necessity of spontaneous activity and inhibitory neuron. This is interesting, since these two biological mechanisms are still poorly translated in machine learning. Surprisingly, when those parameters of the mechanisms of spontaneous activity and inhibitory neuron are matching what is observed in real brains, the model was able to solve trace conditioning, a classical task associated with access consciousness. Complementary to our realistic simulation with biophysical inductive biases, Anirudh Goyal and our colleagues at the MILA have also implemented a simplified version of the global workspace in deep learning. The model involves various subsystems like transformers that compete for attention within a shared workspace where successful information is then broadly shared across the subsystems. You will see in the tutorial how to actually realize this kind of subsystems. The resulting architecture presents advantages in terms of functional compositionality and better generalization after the distribution. And again, during the tutorial, you will have the occasion to play with that. Rufin van Rullen and Ryota Kanai introduced an interesting complementary take regarding the global workspace in deep learning. The global workspace indeed provide a global latent space that forces the alignment at the semantic level across different modalities, enhancing its utility for complex application. Last but not least, another innovative approach is the conscious Turing machine by the Blooms, which use fast information broadcasting among competing processors to handle complex information patterns effectively. Here, they take a theoretical computer science perspective, aligned with the idea of the Turing machine, as a simple model to define and explore computation. Their conscious Turing machine follow as a simple model to define and explore consciousness and the related functions. Parallel to the inductive biases offered by a global workspace, others have also focused on meta-representation. For instance, Axel Kiermans and colleagues have proposed the self-organizing meta-representational account, or SOMA. Here, the second-order network on top of the first-order one creates meta-representation, acting as a form of metacognition and potentially serving as a proxy for consciousness. Another way of looking at meta-representation, and more recently by Ryota Kanai and colleague, in this preprint is to say that instead of having just a second-order information about the first-order information, we can have actually a representation of the process itself leading from the input to the first-order information. And so, in that case, the meta-representational network take as input not the output of the first-order network, like we can see in the label A, but the actual weight and connectivity pattern that leads to the processing of the first-order network. So you can see here that a second aspect would be B, where the input and the first order is then used to build up a meta-representation in form of confidence for a decision. But here, in this new account of meta-representation as representation of processes, the meta-representation network take as input not the first-order information, but the connections and the weights itself. And what they showed is that using this kind of ID, they were able to have a meta-operation network able to classify different networks that were trained to either classify visual information or auditory information. Similarly, the attention schema theory by Michael Graziano parallels this by suggesting that the brain constructs a schema of its attention, improving cognitive performance by allowing more controlled and aware processing. Here, for instance, the fact of seeing an apple is represented as a schema of mental possession of seeing an apple. What is interesting is that they already implemented a form of attention schema in deep learning agents and show that, indeed, having such meta-representation or attention schema helps. Instead of having just the first-order processing of the visual system, they added an attention spotlight that the agent can control. And in this resulting architecture, they obtain better performance in visuomotor tests, similar to catching a ball in a game of Pong, for instance. With colleague at Mila, we have also compared different architecture discussed in the attention schema theory, and we show that having such a controller of attention can improve models' performance in both individual but also cooperative tasks between multiple agents. This illustrates the potential benefits of neuro AI to model and to enhance social ability in artificial intelligence and tackle potentially the alignment problem on the long term. We thus have seen how different cognitive architectures can inform the development of machine learning, moving from empirically grounded biophysical models in neuroscience to more abstract and computational models in AI. However, while we discuss the importance of biological plausibility, we should remain aware that temporal dynamics and embodiment of the social interaction themselves may also be an important part of learning higher-level cognitive function, especially social ones. In our tutorial, we will dive into setting up models based on the global workspace theory and higher-order theories. We focus on their implication for out-of-distribution generalization and the simulation of complex cognitive phenomena like blind sight. Thank you for joining today, and I look forward to our next session.